Next question is number 12. Number 12 says a concave mirror of focal length 25 forms an upright image 4 times as large as the real object. So the height of the image is going to be 4 times the height of the object. We know that. And it's going to be upright. So we can write that down as well. Find the locations of the object and the image. So what we're looking for is the distance of the image and distance of the object. Alright, so if we just plug this into the formulas then, I'm going to use the magnification formula. So height of the image over height of the object equals opposite distance of the image over distance of the object. So what we have is the height of the image is 4 times the height of the object. So I'm going to go ahead and plug that in right here. I'm going to do 4 times the height of the object. Height of the object cancels, and what I find out is I have this relationship then, that distance of the image over distance of the object is equal to 4. Multiply both sides by distance of the object, and we find out distance of the image is equal to 4 times the distance of the object. And I'm going to include the negative there. We now want to use this formula right here. 1 over the focal point, 25, equals 1 over distance of the image, which I'm going to call distance of the image of this, negative 4 distance of the object, plus 1 over distance of the object. So all I did was fill out this equation, and I inserted in distance of the image right here in there. So now we know we're in this row right here because we have an enlarged image that's upright, not inverted. So we have to be in this row with our convex mirror. So we can check this to make sure our answers make sense. But let's go ahead and solve this real quick. I'm going to make this 4 and this 4, in which case I get 3 because this is negative. So 3 over 4 d sub o equals 1 over 25. Now let's multiply both sides by d sub o. And that cancels. And multiply both sides by 25. And that cancels. And I get d sub o equals 75 over 4, which is 18.75 centimeters. And we know that that is going to be in front of the mirror. And then when you do distance of the image, we know it's 4 times as big, but it's a virtual. So multiply that by 4, and you get 75.2. But know that that's behind the mirror because it's a virtual image. So there's our 2 answers. Next problem then is 13. This is a beam of yellow light has a wavelength of 1.425 times 10 to the negative 6 meters in an unknown medium. Part A says, what is the index of refraction in the unknown medium? So here's the formulas, and also in the book we have the wavelength of actual yellow light in a vacuum, which is 5.82 times 10 to the negative 7. So how to find the index of refraction is you just divide the 2 wavelengths. So this is the actual wavelength, which is 5.89 in a vacuum times 10 to the negative 7. And then the wavelength we observe in the medium times 10 to the negative 6 gives us the index of refraction, which in this case is, and this number has to be a typo. What we should have used is this number because we know that the wavelength of light in a vacuum should be bigger than the wavelength in a medium. The wavelength in a medium should be smaller. So that was the wrong value there. If we use this value, then what we get when we do this formula is we get about 2.42, which if you look at that table up in your book, that is a diamond. Next question is 14. It says calculate the critical angles for each of the following. A says a beam of light passing from crown glass into air. So we have crown glass to air. And we have a formula for that critical angle on our formula sheet. Here's right here. So we can do the sine of the critical angle equals n2 over n1. n2 is the refracting medium, and n1 is the incident medium. So n2 is the refracting medium, which in this case is air. That value in the book for n is 1.0003. And then n1 is the incident medium. The incident medium in this case is crown glass. Crown glass is a value of 1.52 in the book. If you do inverse sine of that, you get a critical angle of about 41.1 degrees. Okay, the rest of the questions are the same, so you just have to find these n values for both in the book, and they're on page 486 of your book. Next question is 15. It says the magnifying glass forms an image that is, height of the image is 25 millimeters of a 4.5 millimeter thread. So the height of the object is 4.5 millimeters. When the thread is placed, so distance of the object is 30 millimeters from the lens. What is the focal length of the magnifying glass? What we're looking for is the focal length. So if I grab these formulas, these are the exact same formulas for our lens equation. So we can answer this then real quick. So first we're going to use this formula right here. We're going to plug in height of the image and height of the object. So we get 25 for height of the image over height of the object is 4.5. Set that equal to opposite distance of the image, which we don't know, over distance of the object, which we do know is 30. We're going to solve this for distance of the image. If we do that by multiplying by negative 30 by both sides, we negative 166.6 repeating. All right, so now that we have that, we can use this equation right here to find the focal length. So 1 over f equals 1 over distance of the image, which is the negative 166.6 repeating, plus distance of the object, which we know is 30. If we solve this for f, we get, so hopefully you guys can solve that, but if you do, you get a focal length of 36.6 centimeters. Next question is number 16. 16 says a convex lens with a focal length of 22.5 centimeters is used to create a real object when placed 51 centimeters from the lens. The height of the object is 20 centimeters. Question A asks, what is the image position? So we're looking for distance of the image. So we're using this formula again. 1 over the focal length is 22.5 equals 1 over distance of the image, which is what I'm looking for, plus 1 over distance of the object is 51. Now just subtract 1 over 51 in the calculator and then reciprocate that, and that gives you the distance of the image, which is 40.3 centimeters. All right, then you also want to find the height of the image. So now we're going to use this equation right here. We have the height of the image over the height of the object equals negative distance of the image, which is 40.3, over distance of the object, which is 51. And the height of the image right here is 20. So just flip both sides of this fraction, multiply both sides by 20, and you get the height of the object, which is negative 15.8. That means the object's inverted, upside down. Okay, next question says a beam of light traveling through water strikes the boundary between water and air at an angle of 25 degrees. So that would be the angle of incidence is 25 degrees. We're going from water to air, and that's 25 degrees to normal. So I'm going to draw a picture of that real quick. So here's the picture right here, and then it says at what angle does the light enter the air? So we want to know this angle to normal here, that it enters the air. So we're looking for the angle of refraction there. We can use Snell's law for this, so we're going to have to look up the index of reflection of air, which that is 1.0003 on page 486. And then we also are going to need water, and water is 1.33. So now we can use Snell's law, which is on our formula. Here it is. So this is theta 1, and I'll call this theta 2. All right, so theta 1, N1 is water, which is 1.33 times the sine of theta 1, which is 25 degrees, equals N2, which is 1.0003 times sine of theta 2, which is our refracted angle that we're looking for. All right, so divide both sides by 1.0003, and then also take the inverse sine of both sides. All right, so we're looking for the inverse sine. That will cancel the sine here, and that will give me the angle. So this in the calculator gives you that theta, which is 34 degrees. All right, the last question then, 18, says an object is located 24 centimeters, so that's distance of the object, from a convex lens. The object, height of the image, height of the object is 4 centimeters tall, and its image is -1, so the height of the image is -1 centimeters tall. Where is the image located? So we're looking for distance of the image. All right, we have a simple formula for that, which is height of the image over height of the object equals negative distance of the image over distance of the object. Height of the image is -1, height of the object is 4, opposite distance of the image over distance of the object, 24. Multiply both sides by 24 and divide, and you get the distance of the image is 6 centimeters.